This is a question on free falling, so we must detect that the question tells us air resistance force is negligible, and over here, and therefore this is a free falling scenario. Free falling scenarios have a constant acceleration of 10 meter per second square. So we can represent this using a straight line graph for velocity time. And please draw a straight line graph. Check that you have labeled the axis with V1 and T1 because these are the two data given in the question. The question then asks you to determine what is the value of V1 and T1. So we can set up a simultaneous equation as our strategy. So first up, let's look at the gradient. We know that this is a free falling scenario, so the gradient is constant at 10 meter per second square. So set up our equation to measure the acceleration and equate it to 10. Next, we also know that the object travels a distance of 24 meters. So the area underneath this velocity time graph therefore must also be 24 meters. So we have now set up two equations. You can solve them simultaneously to get the answer. We are back to the empty flower pot again, but right now this flower pot is falling with air resistance. You are to sketch the new velocity time graph, and this is the graph to sketch. There are three features for this graph that I'll run through. First one, in the initial stages of falling with air resistance, the effect on the object is exactly the same as a free falling object. That is when the speed of the object is not fast enough yet, and therefore the air resistance is very negligible. So we represent this on the graph by starting this graph with the same gradient on the velocity time graph, because the initial stages of acceleration is 10 meter per second square. Now, as the object keeps falling, it speeds up. As it speeds up, air resistance force will increase. So imagine a tug of war where there's a downwards weight pulling down on it and an upwards air resistance force pulling up on the object. And as time passes, this upward force becomes bigger and bigger and bigger. You can therefore see that the resultant force on this object will decrease. When the resultant force decreases, the acceleration of this object will decrease, and we represent this in this graph by showing the gradient becoming more and more gentle. The last feature is the horizontal line at the end of the graph that shows constant velocity. This happens when the forces are balanced on this object. The upwards resistance force and the downwards weight has the same value, and we call this terminal velocity. In this part, you are to sketch a new graph for a flower pot that is lighter in mass. So let's think of when does the object reach terminal velocity. The object reaches terminal velocity when the forces are balanced, and this means that the air resistance force must match with the value of the weights of the object. Now, if the weight of this new object is lighter, smaller in value, then the upwards air resistance force doesn't need a long time to match this lower value. Hence, for this lighter object, the object will hit terminal velocity in a shorter period of time. Hence, the green graph is drawn with a smaller value of terminal velocity.